trying to keep it from traveling in a straight line. Quoting Godfather 3, every time it tries to get out, something just pulls it right back in. So in which direction was the tension acting on the stopper?
Inward?
Yes. So as it's swinging around, that tension is pulling it inwards. So there's a force pulling it this way. This is the velocity, this is the force. That force that pulls towards the center has a special name. First off, it's not a new force, it's just a different name for it. The force that specifically is pulling it towards the center is known as the centripetal force. Now, Ms. Sasson pronounces it centripetal, the perfectly fine pronunciation. It's also centripetal. It's less confusing with that other word, which I don't want to name yet. But centripetal force is the force acting towards the center. Matter of fact, centripetal means, well, centra, what do you suspect that means?
Center.
And PET, toward. Toward or towards. One of them's American, one of them's English. I use them interchangeably. All right, it's towards the center. Now we have several words in English where we also have this PET meaning toward. Anyone think of another word that has that PET in it? If two groups come together and then go towards each other, competition, same root. Now let's talk about that other word. The word that's more commonly used, and 99.9% of the time is used wrongly. Centrifugal. It is not a centrifugal force. For Physics 110, probably this will be the last time we talk about it. There is a proper way to use the term. It is usually used incorrectly, so try not to use it, unless you know what you're doing. But again, we have center, and the fugue, fleeing. So that's away from the center. What words do we have in English that have the FUG, which means fleeing? Centrifuge? You said centrifuge? Yeah. It really should be called a centipede, but I was not consulted on that. The word I was thinking of, Grace?
I said fugitive.
Yeah, fugitive. There's also a Latin expression, tempus fugit, which means time flies. It deals with a centrifugal force as a force that points away from the center. But this is pointing towards the center. Typically, this shows up, to do it properly, in what's called a rotating reference frame. So we will not deal with that. That is beyond the scope of this course. So I'm about to erase this, and possibly the last time it ever comes up. Any questions before I erase it and we never speak of it again? Unless a question comes up. All right, so enough of that nonsense. All right, so what we're talking about is centripetal force and centripetal acceleration. Now, of course, there's only so much we like to write. We gotta have a shorthand notation for this. And there is. We've done I hat and J hat to indicate directions. We got a new set here, or actually new letter. And I will pretend that I can write it once. R hat. Now I hat is in whatever direction you want it to be. J hat's perpendicular to that. K hat if you want to go three-dimensional. R hat is a unit vector because we got the hat on it. It's a unit vector pointing away from the center. Whatever center is appropriate. If I wanted to indicate pointing toward the center, what would I do?
Negative R hat.
Therefore, negative R hat. So in the case of my swinging that thing around, I could write the centripetal force, put a little c there to indicate the centripetal force, is negative the tension r hat. This is just shorthand. The negative r hat, again, you put the negative in front even though it's a directional thing. Negative r hat means towards the center, and tension is the actual force. Now, there is a formula for centripetal acceleration. Yes, you could do change in velocity or a change in time. That's true, but there's a, bless you. We could go through some absolutely fascinating math, but I'm going to skip that. Think about you're going around you're driving a car around a curve. How can you increase chances that your car is going to skid a little bit?
Speed up.
All right. So speed definitely affects it. The greater the speed, the greater the acceleration. Because remember, F equals ma, so this would be mass times the centripetal acceleration. So it requires greater force to keep it in the curve if you're going faster, so speed. And for no reason that I've presented other than I'm just going to tell you it's speed squared. And what is the other thing that's going to increase the chances that you will skid?
Like if you make 2 sharp turns with the steering wheel.
So the tighter the radius, the more apt you are to skid. So as the radius gets smaller, the acceleration becomes bigger, and so over r. This is the formula for centripetal acceleration. So if I'm spinning this around, that stopper around in a circle, and I'm just going to make up a mass of that stopper, I'm going to assume that does not work there. Take your guess now whether I'm going to walk out with that or not. Mass of the stopper, I'm just going to say 32 grams. From memory, it's somewhere around there, but my memory's grossly flawed. Which is 0.032 kilograms. The radius, well, let's actually put it into the tube. Is it at the bottom yet? Not yet. Come on. There we go. Now when I swing it, I want to be able to know, I want my radius to stay constant. And so I basically have a piece of tape right here so that as I swing it around, all I have to do is look at that gap right there and make sure that gap stays constant. And also, it will be helpful if I have some tension on here. So let's use 100. And it helps to have coordination too. Let's do it this way. Come on, stay on. Now, if there are no friction, this side should fall, that side should go up. There is friction, so. But if I start it down here and I start spinning it, as I spin faster, notice that piece of tape is going up. So I'm spinning too fast, so we bring it down to 1 to 2 centimeters or so. And I spin it around and I try to maintain a constant speed. Now, I can't help but have that thing swing around. There are certain ways of doing this so it doesn't swing much. But, so right now, as it spins around, I know that there's tension in the string at the bottom. That's why this is not falling. The mass that I have down there, what I'm going to call the hanging mass, M sub H, is, I'm just going to trust the manufacturer for right now, 100 grams. So as I'm swinging it around, I've got this tension in the string. Now, if this is an ideal string, and yeah, granted it's an actual piece of string, but we're going to assume it's ideal. It really does not have much mass. Matter of fact, the mass of this string probably is in the order of a gram. So small compared to the other masses. If it's an ideal string, then the tension on the string here should be the same tension over there. So as I look at it, I've got my stopper right here, swinging about the middle. That tension here should be the same tension at the bottom, and that'll be the weight of this. So I know the hanging weight, mg, 0.1 times, we'll just be generic for right now, 9.8, or 0.98 newtons. So that is the weight hanging at the bottom. We are assuming an ideal string, so that is the tension pulling on the stopper. I know that my centripetal force, and I guess I use this for conservative also, so context, its centripetal force is equal to, well, let's start generically, F equals ma. My centripetal force is equal to mass times centripetal acceleration. So this will be my tension is equal to my swinging mass, M sub S for swinging or stopper, times V squared over R. I know my tension is 0.98 newtons. That's going to be the mass of the stopper, which I threw an estimate of 0.032 kilograms, times my speed squared over R. Well, I can measure R, because I do have a meter stick here. And make sure that the bottom of the tube here is about 1 centimeter or so from the tape. And I'm measuring the distance to the top here. So I go from the center of mass of an estimated center of mass to here, and it pulls a little bit. And 72.5 centimeters. So R, 72.5 centimeters, or 0.725 meters. So the math problem we're working with here, it's 0.98 equals 0.032 times v squared over 0.725. Several ways of solving it, but again, we're trying to get to v, so let's start getting rid of the fluff. Let's get rid of the 0.032 first. How do we get rid of it?
Divide.
That's the one over 0.032 over 0.032. And what is this? Someone be kind enough to calculate that?
$30.625.
30.625. All right. So v squared over this is equal to that. So how do we get rid of the 0.725? Yeah, so we multiply both sides by 0.725. So v squared is equal to whatever that is.
22.
Say it again.
22.203.
And so v equals,
Square root of
yep,
22.203. Oh, do you want me to give you the answer?
square root of 22.203.
$4.712
All right, units.
meters per second.
All right, so we know how fast that, ideally, that stopper needs to go, assuming that my numbers are all right. But how do we figure out the speed? How do you find the speed of an object that's swinging around in a circle? All right, how else can you find speed? What's the formula?
Change in position. Or
Speed, not velocity.
Distance over time.
Yeah, distance. You're on the right track, but the other one. So my speed is distance divided by time. I know what it's supposed to be over there, so that is going to be my distance divided by time. So I have this thing traveling in a circle. What is the distance around a circle?
Radius. Diameter.
Diameter is that far. Radius is that far.
Circumference.
Okay, that's the word. All right, so what's the formula for circumference of a circle?
Pi.
All right, we got pi times what?
Pi times radius? Is that it?
isn't it pi times like 2r or something like that?
Yeah, pi times the diameter, or pi times 2 times the radius. So this is just going to be 2 pi times the radius divided by time. Now I did a capital T here. This is the reason I don't use T for tension. I use a capital T here. This, when you see a capital T, this is period. And period is the time or one cycle of repetitive motion. So I have this thing Schwartz going around in a circle a bunch of times. The period is just how long it takes to go around once. So let's figure some stuff out here. We'll see how close we actually get to that number over there. So this is 2 pi times my radius. well, I already figured out my radius, that's 0.725 meters. And we have to figure out the period. Now, to figure out the period, we need to time it. However, you don't want to time it just once. You need to time it several times, just so any issues with the reflex get sort of washed out. So what we're going to do here is I'm going to swing it around and get out your timers, which for most of you is, well, for probably your phone. Good. I need to put this on the bottom. Let me get going, and then we'll do a count in the starting. We're going to time 20 revolutions. So first, I want to make it as horizontal as possible, which is above my head. And now, when I'm actually doing the timing, I should not be touching this or pulling on it. All right, not yet. Okay. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20-ish. All right, so for 20 revolutions, what times do we get?
18.36.
18.36.
18.17.
18.17.
7.2.
17.
17, same, okay.
18.14.
18.4.
14.
18.14.
14, yes.
Anyone else?
18.02.
18.05.
Any others? Now, ideally, you would have done your own counting. You would have picked out a point where it's right in front of you, and you would have counted. And that'd be better on the timing than Mike doing the counting for you.